Because there's no loss when the light is reflected off the sides of the fibre, and the fibre is made from super high purity glass, signals can travel huge distances without too much attenuation, although stations are needed to reform and amplify the signal from time to time. The actual lasers that are used in communications are infrared at about 1500 nanometers, because that's where the absorption of the glass is at a minimum. So all of the pictures you see of fibres with pretty light coming out are actually misleading. In physics, we often present refraction problems as if the refractive index was a constant for a material, but in fact, it depends on the wavelength. This means different colours of light will see different refractive indices, and so will be slowed down and bent by different amounts. This separating of white light into colours is called dispersion. One way of doing it is with a prism. Refraction happens in prisms, and the higher the refractive index of the prism, the greater the angle of deviation from the original path will be. This is what dispersion in a prism looks like. All of the white light has been refracted as it passed the surfaces of the prism, but the violet light has been bent more than the red, and so we see the light spread into a rainbow. This is what we call chromatic dispersion, in other words, deviating because of different colours. This gives you an idea how refractive index changes in a few different materials. Note that it's always higher at the smallest wavelength end of the spectrum, so violet light is always bent the most in a prism. Here you can see on the left, the violet light has deviated the most from its original angle. But what if we use a source that is just one wavelength? You can see on the right that we can't disperse laser light because it isn't a mixture of wavelengths, it's just one. So light is refracted at just one angle. You can see at the top there the different outputs of white light, which is the red light, and what we call a continuum, meaning it's a big range of different wavelengths, versus the laser light that is the blue peak there, that is a very, very narrow range of wavelengths. So that's why we need lasers for long-distance communication in optical fibres, because white light will actually travel at different speeds, and so one end of the visible spectrum will arrive first and the other end will be last.